So hello everyone, today we are here to discuss about quicksort algorithm. So basically it is based on divide and conquer technique, which says that we divide the problem in small part and solve the smaller part of the problem and then combine it again. So what we are actually going to do here is we are going to take an element as a pivot element, and then we are going to sort the array around the pivot element by partitioning it. We will partition the element and we will take a pivot element, and then we are going to sort it around it. Then the time complexity is basically order of n log n. We are going to discuss this in the later part. Here is a flow chart which completely describes the quicksort algorithm. Let's say here is an array which has these following elements, and this is the start index of the array and this is the end index of the array. We take two variables here. First is the idx, which is first initially set as start minus 1, which is here, because start index is always 0, so we are setting it at minus 1 because initially we do not want to swap anything or change the position of anything, so we are initially putting it at minus 1. And another variable is j, which is used for looping in this for loop. So let's see by the example. First we have 5 2 6 4 1 3. For here, for example, we are taking 3 as our pivot element. So this is a pivot element here. In first situation, the j will be here and idx will be at minus 1. So what the algorithm says is basically, if here we have the condition, yes, if j is smaller than pivot element, means j is here and pivot element is here, means if 3 is if 5 is smaller than 3, then swap. If 5 is smaller than 3, no. Here the condition is false. This means we have to move forward, means j plus plus. So what we are doing here, let's add it here. Here what we are doing, j plus plus, as the condition is false. Okay, then the j is here. Now idx basically was here itself. Then we were comparing then we are comparing 2 with 3, means j is here. Okay, let me move the j is here now. Then 2 is being compared with 3, so 2 is compared with by 3. Then whenever this condition is true, hence in this case it is true, then what we are going to do, we are going to increment the value of idx. So here we have incremented idx here, and then we are swapping the array of idx with j, means what we actually want to do is we want to set all the smaller values than the pivot element at the left of the pivot element and the larger values at the right side. So idx is going to make space for the smaller elements here. So we are swapping the idx with the arr of j, means we are swapping 5 with 2, so this is the array. Now this step again, then it will compare the j with the pivot element. How pivot element is 3, then it compares 5 with 3. 5 is greater, then move forward. Then j is here, j is here. J is compared with 3, 6 is compared with 3, and again move. Then it is compared here, again compared by 4, it is also greater. Then it is compared by 1. In this situation what happens is basically if 1 is smaller than 3, so what is happening is that idx moves through the index 1, means idx plus plus, as idx was initially at 0, then idx plus plus, then the idx moves to this position, and then we are swiping idx with the j. So j and idx is swapped. In that situation, the 1 will come here and then 5 will go here. So this is the main format in which we are going to swap uh, in reference to the pivot element. So what happened is, all the smaller elements, then the pivot element, then the pivot is moved to the left, while all the greater elements are at the right. Now what we want is, we want to get the correct position of the pivot element. So what we are going to do is, in that situation also we are going to make idx plus plus and then swap the ARR of IDX. ARR of IDX means here with the and why and, because we are taking the pivot element as the last element. Here we have decided that ARR of and is going to be our pivot element, and starting index is going to be IDX is going to be start minus 1. Okay, so now we are going to see what happens after this. So as it is a divide and conquer technique, in this now it will partition the sub arrays of it. Means after this we know that the pivot element is at its correct position. So this part means the this 2 and 1 will be separated, and 4 5 6 will be separated, not exactly separated, but means this part is considered at the left sub array and this part will be considered as the right sub array. So now again a pivot element will be considered. So now how we will discuss the decide the index. So index here will be starting, and here will be pivot minus 1, and here will be pivot plus 1 will be the starting index, and ending index will be end. Then again the last element means the element at the pivot minus 1 index is going to be our pivot element. Then we will compare the pivot element with the idx is again at 0 minus 1 position. Then if it is smaller, then if it is smaller, then it would swap, but it is not, then it will remain at its same position. But as all the elements are completed and we are on the pivot element itself, then this condition will be true in this case here, this one. Then we are swapping the idx with the ARR of n. So we are swapping the this will be our idx, and this is our ARR of n, both will be swapped, and this condition, and here then we will again separate it, and then 1 will be separated, 2 will be separated, and we know that a single element is always sorted. Okay, the same will happen in the right subarray. So how this is happening in the left and the right subarray? This is because we are calling this partition function, this quicksort function recursively. Again and again we are coming here. If what we are doing is, if the starting index is smaller than n, starting index means if the starting index means this index is smaller than n, till then only we are going to perform this recursion. This is a base condition here. Okay, so here what we are going to do is partition the array. So for partitioning we have this another function, and then we are using the recursion to call the quicksort on the left subarray and quicksort on the right subarray. And here we are passing a array, our starting index, our ending index of the left subarray, and again in the right subarray we are doing the same thing, pivot index plus 1, which is the starting point of the right subarray, and the end. In this way the quicksort function will call itself again and again for the left and the right subarray, and then we will finally get our complete array. So now let's discuss about the time complexity of this quicksort function. So what happens is, here we have a complete loop, right? For int j is equals to st and j is smaller than and. So and is basically the size of the array. So this loop is working till n. So let's denote here that it will go till n. So the time complexity of this loop is going to be order of n, and as we know that each time the array is going to be half, like it is going to divide. When we are partitioning here, then after this, whenever we are calling the quick sort for the left and the right, so what we are basically is happening is here is first it will traverse the whole, then it will divide in half, and then half, and then half, and half. So we cannot take it n. Then when we divide it in the half, the time complexity turns out into order of log n. So here we can mention it, the time complexity will be in order of log n. So this is a very important technique or sorting algorithm. And what happens is, why it is better in terms of comparison by the merge sort, that is because it does not require any external array to store the sorted part or any part. Hence the space complexity is order of 1, as it does the in place sorting, means it will sort at its own place. This is all it is not like that it is dividing and storing it in another array and this in another array. No, it is storing this complete it is doing it on its own place. Hence the time complexity is order of n log n, as the for function has this order of n, and the quick sort calling was log n, and the space complexity is order of 1. But it is not considered very stable, and in this the pivot choice matters for the performance. Why it is saying like this? It is because let's say if it is an sorted array, so the last element is always going to be the greater one. Means let's say in our situation it is going to be 6. So for this function it could take order of it can create a one-sided array, or we can say one-sided tree. So one-sided recursion tree. In that situation the time complexity is going to be order of n square. That's why it is very important to choose the pivot element properly. That's all for the quick sort. Now we can see the code here. Here we have the quick sort code. So here is the same function which we had, the partition function and the quicksort function. The quicksort function again and again calls for the left and the right subtree. Here we pass the quicksort function, and then the partition is being happening. Now one another thing I want to add on is that just when we want to make the resultant array as the descending order, then we are going to just change this condition here. So let me run it for you. So it is going to run, and here is our output. Okay, so that's all from my side. Thank you.